So if you're starting with the first one, you're guessing the genders of 3 children in a family. All right, how many choices are there when someone has a child? 2. Boy, girl. It's like flipping a coin. First time through, you can get a boy or a girl. Second time, boy, girl. Boy, girl. Third child, boy, girl. Oops. We're not working right now. How many possibilities were these? 2 times 2 times 2. How many possibilities? How many outcomes? 2 times 2 times 2. 8. 8 outcomes. So when you come down to this, you should have 8 ends here. 1, 2, 3, 4, 5, 6, 7, 8. Now, your sample space, go all the way across. BBB, boy, boy, boy. BBG, boy, boy, girl. BGB, BGG. This is how you're going to make your sample space. Girl, boy, boy. There's a difference between a boy, boy, girl and a girl, girl, boy, and a girl, boy, boy, because order makes a difference here, what order you have them in. Girl, boy, girl. Girl, girl, boy. And girl, girl, girl. Now, the event that I want is how many times does the family have 2 boys? How many 2Bs are there? Here's one. In case you can't read my writing, there's one. There's one. How many times did this occur? 3 times. So therefore, what is the probability? It only occurred 3. That's what they were looking for. But what is the probability of them, out of 3 children, getting 2 boys and a girl? 3 out of 8. So your probability is there's 8 things total, and you wanted 3 of them. How many ways can I get this? 3 different ways. Do we see the difference between ways and probabilities? Okay? All right. A student must choose from 7 classes to take at 8 a.m., 4 classes to take at 9 a.m., 3 classes to take at 10 a.m. How many ways can the student arrange their schedule? What principle is this? The fundamental counting principle. Good. So what do? Multiply that. 7 times 4 times 3 will give you 84 different ways to make your schedule. Okay. Counting principle. I have 5 shirts, 3 pants, 2 shoes. So 5 times 3 times 2. Counting principle. How many different ways can you do this? God bless you. Okay, label these guys. I left the answer to this one. 9 through 11. I want to know if it's a subjective, empirical, or classical. Okay. Empirical is the same as your experimental. That's what you do from your experimental. Classical is the same as your theoretical. That's been proven over time. It's not going to change at all. And your subjective has a little bit of your gut feeling, kind of like if you were listening to the news report for this storm that's supposed to come in tonight. It's subjective. Well, depending on what goes on and who you listen to, so they got a little bit of subjectivity. So if somebody watching says, okay, I think this is gonna happen, I've seen it in the past. Somebody else says, I'm not sure of that. Okay, so the chance that A's Corporation stock will fall today is 75%. What type of probability is that? No. Subjective. Subjective. If it was empirical, they would be just looking at, like, today, but they're looking at other things, the market in general, the patterns that they read. That would change. Like, they threw this in to say, yeah, probably. The probability that a person can roll his or her tongue is 70%. No, that's empirical. How do you think they came up with that? How would you think? 6. Well, maybe they're asking people in this room, can you roll your tongue, yes or no? So out of 24 people, say 8 people say yes. 30% of my class says they can roll their tongue. Now a different group of people come in, and I ask them, well, about a 24 said yes. That's my experimental part. And this one, I left the answer there. The probability of rolling a 2-sided dice and two 6-sided dice and getting some greater than 9 is 1 out of 6. This is your classical. This is not going to change. And remember I showed you with the dice, an easy way to do it? Come all the way down. And then we did patterns. This is the sum. Okay, so to getting greater than 9, you'd have to keep on going and you'd count your pieces greater than 9. That's not going to change, no matter how many times you do this. God bless you. A 6-sided die, still, God bless you, has 1 through 6. God bless you.
And
okay. All right. Okay, here's a good one. Reading off your charts. Find the probability that a randomly selected firm will have at least 10 employees. First thing, are these categories mutually exclusive?
no, yes, yes, they are.
Mutually exclusive means they have nothing in common. Like, mutually exclusive means you can't be both at the same time. That's your Venn diagram that does this and this. Mutually exclusive. If they're not mutually exclusive, they overlap. They have something in common. So, in this category, can your number of employees be 1 to 4 and 10 to 19 at the same time?
No.
No. They're mutually exclusive. They're independent of each other. Okay? So, therefore, find the probability that we'll have at least 10. We want 10 or more. So we're going to add these pieces up. These are mutually exclusive. There's no overlap. So it's the probability of the 10 to 19 plus the probability of the 20 to 99 plus the probability of the 100 or more. We're just going to add them all up. Nothing's in common here. It's mutually exclusive. They're independent of each other.
You just add those percentages.
Add those up. And or you add, and you multiply. Now the or, remember the or though, if they're not mutually exclusive and they have an overlap, you have to subtract out your overlap. Remember that? Well, hopefully I think there is one in here. So find the probability that there are fewer than 20. So which ones am I looking at? Less than 20. Should I count this category?
No.
No. So I'm going to add up these. And they're mutually exclusive, so you just add them up again. And you can leave them in percents. They're already in percents. You can leave them in percents. If you want to move them to a decimal, move your decimal 2 places to the left. Remember doing these? A little. Mutually exclusive on the ors, you just add them. Remember doing these, the givens? Okay? Find the probability that a student failed given the student took the exam for the first time. So, if this is my given, this is the one I want to circle, the given part. Took the exam for the first time. So I can't leave that blue row. Circle it, whatever's given. Now, find the probability that the student failed. Which one is failed?
Second row.
Second one. Over total. Over the total. How many decimal places do our probabilities go? 3. I want 3 decimal places. Make sure you're round. So 0.317. Okay? Now, this one's different. Find the probability that a student repeated the exam given that the student passed. That's the part we want to circle first. Pass. So we come to the pass column. I can't leave that column. Everything that I look at is in that column. Repeated, 407. Out of what? 48, 34. Good. And so you get your probability. Remember the givens? Go for the given first. Now, sometimes the given comes first in the sentence. Regardless of where it comes, that's the part that you circle. Sometimes they play with the words a little bit on you. Given that the student has failed, what is the probability that they repeated the exam? Whatever the given says is the part you circle. Agree? Write yourself a little note. This is how you study. You remember the rules to these things. Not just one specific example. Remember the rules to this. Okay. Your sock drawer has 18 folded pairs of socks with 8 pairs of white, 6 pairs of black, and 4 pairs of blue. What is the probability, without looking in the drawer, that you first select and remove a black pair, and then you select and you remove either a blue or a white? If I'm removing and not replacing, are they dependent or independent? Dependent. And when they are dependent, your probability will change. Okay, so now, easiest way to start, guys, is like this. Pull these out. 8 pairs of white, 6 pairs of black, 4 pairs of blue. I'll put a U for blue. Altogether, you have 18 pairs of socks. How many pairs are you going to actually remove? How many times are you removing a pair? 2. So, they're dependent of each other, so things are going to change. So order makes a difference when I do this too. Well, really, but the bottom numbers will. So my first pair I want to be black, and my second I want either a blue or a white. And what do we do on an or? Add. On an or you add. But okay, I'm sorry. This is an and over here, yes. But I'm sorry, I was looking at this or. So okay, so those of you are still looking at the and for the problem. Yes, you multiply. Okay, so the probability of a black first time around is what?
6 and
Okay, remember, because they want probabilities. 6 out of 18. Now, I'm holding this black pair of socks. I don't put it back. I remove it. I have one less black. This is the easiest way to do this. One less pair, right? And now I have 17 pairs and only 5 blacks remaining. Now I want to find what is the probability of a blue or a white. This is where I add blue and white. 12 over, good, 17. And that's a multiply because I want both at the same time. Put it in your calculator, put your fractions in parentheses and multiply. Multiply the tops, multiply the bottoms, whichever way you like to multiply. Use your fraction key and give me 3 decimals. Okay, I tried to pick ones that we've done over this whole chapter. That kind of represent the things that we've been doing. Now, when you approach these problems, think independent, think dependent, think does your probability change, is your probability remaining the same? Think if it's an or, think if it's an and. Put your lines out. If you find you're doing this twice, put your lines out. That's going to help you. Make this right here. Without this, really, that's hard because you got to keep going back to the words, especially if they write out 8 instead of the number 8. You got to keep looking at them again and again. Once you pull your information out, you should be a lot better off. Okay, number 29. In a random sample of 250 working adults, it found that 74% access the internet at work, 88% of them access the internet at home, and 72% access the internet at both work and home. Find the probability that a person in the sample is selected at random, accesses the internet at home or at work. So start with your probability. At home or at work. On an or, what do? We add. Now, think of your Venn diagram. If I'm doing a Venn diagram for this, how many circles do I have? 2. And what are they? Home and work. Do they overlap at all? Is there any place that uses both home and work?
Yeah.
Ah, right here. This is where they overlap. So are they mutually exclusive? No. So you see this piece right in here? Well, you counted it for the home circle. You counted it for the work circle. So you counted it twice. So this is the case we have to say, subtract the probability of home and work. This is the overlap. They're not mutually exclusive. So easiest way to do this is flip them to a decimal. Here's your at work, 74%. Here's your at home, 88%. And your overlap. Okay, now here's another thing. If we didn't take that out, doesn't that probability add up to more than 1? Could your probabilities be more than 1? No. So don't forget to take this out. 72% is an overlap. On an or, you're adding, but because they had something in common, you have to subtract out what they have in common. And this comes to 0.9, or 90%. This was a big difference from the old book because it was like in the 40s, and 30s, or 20%. This is really up the percentages on these. Okay, everybody try number 31. Try 31.
What it acts between here and 8 do we count for and 8?
Because it says inclusive, yes. If it says non-including, no. Inclusive, yes. This is a tough one. Set up your probability statement first. What are they asking for? The probability of what? Or, okay. So, what is the probability that, first of all, how many cards in your deck? 52. 4 through 8, inclusive. So we want all the 4s, all the 5s, all the 6s, all the 7s, all the 8s. We want all 5 of those things. How many suits are there? 4. So I've got how many 4s? 4 4s, 4 5s, 4 6s. So therefore, how many cards meet that criteria? 20. Let's hold the bottom number for at the end, 52. probability that they're clubs? How many clubs in your deck? 13. Now, did we have any instances where there was a 4, a 5, a 6, a 7, and an 8 that was also a club?
Yes.
Ah, how many of them?
5.
5. So what do I do with that? Subtract it. Isn't it easier when you lay out your probability statement to see what is it I want to get? It's right there in that last sentence. Okay, so you get 28 out of 52, 0.538. And Dan had a good point. If it says inclusive, you count them. If it says in between them, you don't count them. Or they'll say not inclusive. Here's another good one. A card is randomly selected from a deck of 52. Find the probability that the card is red or queen. So how many reds in your deck? And then, or we do what? Add. How many queens in your deck? Now, is there a possibility that I have queens that are red?
Yes.
Ah, 2. What do I do with the 2? Subtract them. This is where you take the probability of a red queen out of there. You counted it twice. You counted it as red. You counted it as a queen. So again, 28 out of 52. Okay, is everybody seeing this? 0.538 again. And it just happened to turn out to be that number. It has no bearing on the one we did before. It just happened to come out to be that number. Okay, here we get to permutations now. A little bit on permutations. Which one does order matter? Permutations or combinations? Permutations. Permutation says order matters. I have 15 cyclists enter a race. In how many ways can they finish first, second, and third? Permutation or combination? Permutation. Easiest way. You want 3 places? 1, 2, 3. How many can come in first? How many then second?
14.
Then third?
13.
And what do you do with these numbers? Multiply them. Can you set me up a permutation? P?
15.
Good. 15P3. Okay, I don't want 15 factorial because I only want to judge those 3 places, not the whole thing. 5 players, that's easier for me to read it down here. 5 players on a basketball team must choose a player on the opposing team to defend. In how many ways can they choose their defensive assignments? How many players are on the other team? 5 factorial. So you could set it up this way first. Do your 5 lines. 5, then 4, then 3, then 2, then 1. Give it to me in a permutation. 5P, 5. Okay? Because order matters. Order matters which way you choose.
So, anyway you do the same answer?
Yes, any of those ways. So, I like, if you struggle, put the lines down. Even if it's a large number, even if it said like 26 players and you're doing 26 if as soon as you start writing 26, 25, you're going to realize it's 26 factorial, or you're going to be able to set the P up 26P26. But you don't have to write the whole thing out. It just kind of helps you see where you're going with that. Because sometimes we do 3 positions, sometimes we do all positions. Okay? Good? That was a good question. Okay. An employee must hire 2 people from a list of 13 applicants. In how many ways can an employer choose to hire 2 people? Does order matter?
No.
No. So what are we looking at? C. How many people to choose from?
13.
How many do they want?
2.
2. So put that in your calculator. And this just said how many ways. Remember, it could also say how many different ways. Different does not mean permutations. It just means each way is unique. So 78 ways. Wait, say that again? Is that it? Yeah. Okay. No. 13 things taken 2 at a time. That means 13 times 12 over 2 factorial. Just put it in your calculator. No. 13 times 13, if it was in a line like this, but you replaced your employers, you're not replacing them either. And it doesn't matter what order you choose. A security code consists of 3 letters followed by 1 digit. Start like this. Letter, 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 digit. The first letter, how many letters are there in the alphabet? 26. The first one cannot be any of these 3. So what can they be? 23. What is the probability of guessing the code in 1 trial? Are there any other restrictions that we can spot? So how many letters for the second one?
26.
Then, how many digits? 10. Even though it's 0 through 9, that's your 0, that's your 10. That's your 10. Now, it asks the probability. So these are how many ways can I do this? So this gives me how many ways? A heck of a lot of ways. What is the probability that you guess it the first time? 1 out of that number.
You don't know how to convert that?
Well, yeah, you can leave it like that because it can't be reduced.
Yeah.
Or you could give it to me in a 3-digit decimal, that's fine. Everybody see the difference between ways and probabilities? Yes. That's important. How many ways, how many probabilities? Okay. Here comes your favorite defective things. You might see this kind of problem again. Defective, not good, like something's wrong with it. Out of 200 calculators, I have 3 defective calculators. The calculators look the same. Right, so does it matter what order I pick anything up in?
No.
No. So right away I know I got combinations. And I want to pick a sample of 3 of those calculators. Find the probability that there will be no defective calculators. Start like this, guys. You have 3 defective. So how many are not defective? These are good. Or not defective. So, probability. All of these have probabilities. What's going to be my bottom number for selecting any 3? Okay, there's my bottom number. No defectives. How many are not defective? 197, C3. Find a probability that they are all defective. How many defectives do you have? 3, and you want 3 of them. There's only one way that can happen. And there's your bottom number. Your bottom number stays the same. Find the probability that you get at least 1 defective. At least 1 defective means 1 defective, 2 defective, or 3. What's the only case that doesn't happen? No defectives. So use your 1 minus whatever this guy is. Okay?
Is there another way you could do that?
In this case, well, not yet. Not yet, but we will in the next unit, but not. Well, what you want to say in this one is this. I can have 1 defective, I can have 2 defective, or I can have 3 defective. The only thing that I can't have is no defective. So if I take my complement, 1 minus no defective, I get my answer. And the opposite for this. Take this 1 minus this thing. Test is tomorrow.